Hi, so today I'm reading a little bit older paper from 2016. It's called Professor Forcing, a new algorithm for training recurrent neural networks. This one is from multiple people: Lamp, Goyal, Zhang, Courville, Joshua Bengio, Université de Montréal. Yeah, all of them. So this teacher forcing is an algorithm for training recurrent networks. This sort of I think, in short, it doesn't allow the network to go too far away from the sort of training from the training data. So the abstract: the teacher forcing algorithm trains recurrent neural networks by supplying observed sequence values as inputs during training and using the network's own one-step ahead prediction to do multi-step sampling. We introduced the professor forcing algorithm, which uses adversarial domain adaptation to encourage the dynamics of the recurrent network to be the same when training the network and when sampling from the network over multiple time steps. We apply professor forcing to language modeling, vocal synthesis on raw waveforms, handwriting generation, and image generation. Empirically, we find that the professor forcing acts as a regularizer, improving text likelihood on a character level, Penn Treebank, and sequential MNIST. We also find that the model qualitatively improves samples, especially when the sampling for a large number of time steps. This is supported by a human evaluation of sample quality. Trade-offs between professor forcing and scheduled sampling are discussed. We produce T-SNE showing that professor forcing successfully makes the dynamics of the network during training and sampling more similar. Okay, so the goal is to make the sampling during training and sampling more similar. Okay, let me find main contributions. Okay, here. Our work provides the following contributions regarding new training framework. We introduced novel method for training generative RNNs called professor forcing, meant to improve long-term sequence sampling for recurrent networks. We demonstrate that with human evaluation of sample quality by performing a study with human evaluators. We find that the professor forcing can act as a regularizer for recurrent networks. This is demonstrated by achieving improvements in test likelihood on character level Penn Treebank. Sequential image generation, speech synthesis. Interestingly, we also find that the training performance can also be improved, and we conjecture that it is because long-term dependencies can be more easily captured. When running RNN in sample mode, the region occupied by the hidden states of the network diverges from the region occupied by the when doing the teacher forcing. We empirically study this phenomenon by using T-SNEs and show that it can be mitigated by using professor forcing. Region occupied by the hidden states of the network diverges from the region occupied when doing teacher forcing. Okay, in some domains, the sequence available at training time are shorter than the sequences that we want to generate at test time. This is usually the case in long-term forecasting tasks, climate modeling, econometrics. We show how using professor forcing can be used to improve performance in this setting. Note that the scheduled sampling cannot be used for this task because it still uses the observed sequence as targets for the network. So I will first go quickly through the paper. I think I will just do a quick overview. So proposed approach, professor forcing, related work, experiments, sequential MNIST, and okay, conclusion. And I will get back to the whole article, but for those who stay only for a few minutes, I will read all this. The idea of matching behavior of model when it is running on its own, making prediction, generating sample, etc., versus when it is forced to be consistent with observed data is an old and powerful one. In this paper, we introduce professor forcing, a novel instance of this idea when the model of interest is a recurrent generative one, which relies on training an auxiliary model, the discriminator, to spot differences in behavior between these two models of behavior. A major motivation for this approach is that the discriminator can look at the statistics of the behavior and not just the single-step predictions, forcing the generator to behave the same when it's constrained by the data, and when it is left generating outputs by itself for sequences that can be much longer than the training sequences. This naturally produces better generalization over samples that are much longer than the training sequences, as we found. We also found that it helped to generalize better in terms of one-step prediction, log likelihood. Okay, let me backtrack once more. Is that the discriminator can look at the statistics of behavior and not just the single-step prediction, forcing the generator to behave the same when it is constrained by the data and when it is left generating outputs by itself for sequences that are much longer than the training sequences. Okay, let me continue. We have also found it has helped to generalize better in terms of one-step prediction, log likelihood, even though we are adding a possibly conflicting term to the log likelihood training objective. This suggests that it acts like a regularizer, but a very interesting one because it can also greatly speed up convergence in terms of a number of training updates. We validate the advantage of professor forcing over the traditional teacher forcing on a variety of the sequential learning and generative tasks, with particularly impressive results in acoustic generation, where the training sequences are much shorter because of the memory constraints than the length of the sequences we actually want to generate. Okay, I'm going back to the introduction. Recurrent neural networks, RNNs, have become the generative models of choice for sequential data, with impressive results in language modeling, Mikolov 2010 and Mikolov Zweig 2012, speech recognition, Bahdanau 2015, Chorovsky 2015, machine translation, Cho et al. 2014, Sutskever 2014, Bahdanau 2014, handwriting generation, Greece 2013, image capture generation, Xu 2015, Chen and Lawrence Zitnik 2015, etc. RN models the data via fully observed directed graphical model. It decomposes the distribution over the discrete time sequence y1 and yt into the order product of conditional distributions over tokens. By far the most popular training strategy is via maximum likelihood principle. In the RNN literature, this form of training is also known as teacher forcing. In 1989, Williams and Zipser, due to the use of the ground truth samples being fed back into the model to be conditioned on for the prediction of later outputs. These fed-back samples force RNN to stay close to the ground truth sequence. When using RNN for prediction, ground truth sequence is not available. Conditioning, and we sample from the joint distribution over this sequence by sampling each yt from its conditional distribution over the previously generated samples. Unfortunately, the procedure can result in problems in generation as a small prediction error compound in conditioning context. This can lead to poor prediction performance at RNN's conditioning context. The sequence of previously generated samples diverge from sequences seen during training. Recently, Bengio 2015 proposed to remedy that issue by mixing two kinds of inputs during the training. Those from the ground truth training sequence and those generated from the model. However, when the model generates several consecutive YTs, it is not clear anymore that the correct target in terms of its distributions remains the one in the ground truth sequence. This is mitigated in various ways by making the self-generated subsequences short and annealing the probability of using self-generated versus ground truth samples. However, as remarked by Hutzar 2015, scheduled sampling yields a biased estimator. Indeed, even as number of examples and the capacity to go to infinity. This procedure may not converge to the correct model. It is, however, good to note that the experiments with scheduled sampling clearly showed more improvements in terms of robustness of the generated sequences, suggesting that the something indeed needs to be fixed or replaced with the maximum likelihood or teacher forcing training of generative RNNs. In this paper, we propose an alternative way of training RNNs which explicitly seeks to make the generative behavior and teacher forcing behavior match as closely as possible. This is particularly important to allow RNN to continue generating robustly well beyond the length of the sequences it saw during the training. More generally, we argue that this approach helps to better model long-term dependencies using a training objective that is not solely focused on predicting the next observation, one step at a time. Our work provides the following contributions regarding new training framework. We introduced a novel method for training. Yeah, I went through these, right? So, proposed approach, professor forcing. The basic idea of professor forcing is simple. While we do want the generative RNN to match the training data, we also want the behavior of the network, both its inputs and in the dynamics of the hidden states, to be indistinguishable, whether the network is trained with the inputs clamped to a training sequence, teacher forcing mode, or whether its inputs are self-generated, free running generative mode. Because we can only compare the distribution of these sequences, it makes sense to take advantage of the generative adversarial networks framework, GANs, Goodfellow 2014, to achieve that second objective of matching two distributions over the sequences. The one observed in teacher forcing mode versus the one observed in free running mode. Hence, in addition to generative RNN, we train a second model, which we call the discriminator, and that can also process variable length inputs. In the experiment, we use bidirectional RNN architecture for the discriminator, so that it can combine evidence at each time step from the past of the behavior sequence as well from the future of that sequence. Okay, so the proposed approach. So they are afraid of train the model in one mode and then in free running mode being these two being too different. They want to make the training more similar to the actual free running mode. So they only want to compare the distributions of the sequences, right, of the correct one and the generated one. And to do that, they use GANs as in sense of Goodfellow 2014. So they add a second model, which is called Discriminator, which also process variable length inputs. They use bidirectional RNN for discriminator, and it combines evidence each timestamp from the past of the behavior sequence as well from the future of the sequence. Okay, definitions and notations. Let the training distribution XY pairs of the input and output sequences, possibly there are no inputs at all, and output sequence Y can also be generated by generator RNN when given an input sequence X. Okay, I'm gonna go through this faster. Behavior sequence B is either the result of running generative RNN in teacher forcing mode, with Y as the training sequence of input, or in free running mode, with Y self-generated according to P probability of theta G Y conditioned on X, with X from the training sequence. Note that in this case the generator does not simple condition. Training objective. The discriminator parameters theta d are trained as one would expect. That is, to maximize the likelihood of correctly classifying a behavior sequence. Practically, this is achieved with the variant of stochastic gradient descent with mini batches formed by combining n sequences obtained in teacher forcing mode and n sequences obtained in free running mode. Okay. So they have this discriminator which is trying to detect whether the generator is running in teacher forcing or free running mode, and they try to make it as hard as possible to distinguish these using the adversarial setup. Okay. Professor forcing is an adversarial method for learning generative models that is closely related to generative adversarial networks and adversarial domain adaptation. Our approach is similar to generative adversarial network GANs because both use discriminative classifier to provide gradients for training generative model. However, professor forcing is different because the classifier discriminates between the hidden states from the sampling mode and teacher forcing mode. So the discriminator looks at the hidden states and not the outputs, whereas the GANs classifier discriminates between the real samples and generated samples. Okay. So the professor forcing uses a GAN. They use this adversarial network, which looks at the hidden states of the generating network and tries to find out whether it is running in teacher forcing mode or free running. It does not look at the outputs of that as in normal GANs, but on the inner states. One practical advantage of professor forcing over GAN is that the professor forcing can be used to learn generative model over discrete random variables without requiring approximate backpropagation for the discrete spaces. The adversarial domain adaptation is classifier to discriminate between the hidden states of the network with the inputs from the source domain and the hidden states of the network with inputs from the target domain. However, this method was not applied in the context of generative models. More specifically, was not applied to the task of improving long-term generation from recurrent neural networks. Alternative non-adversarial methods have also been explored improving the long-term generation from recurrent neural networks. The scheduled sampling method, Bengio 2015, which is closely related to CERN 2009 and Dagger 2010, involves randomly using the network's predictions as inputs, as in sampling mode, with some probability that increases over the course of training. This forces the network to be able to stay in a reasonable regime. Okay, what they use? Using the network's predictions as inputs, as in sampling mode, with some probability that increases over the course of training. Forces the network to stay in a reasonable regime, receiving the network predictions instead of observed inputs. While scheduled sampling shows improvement on some tasks, it is not consistent estimation strategy. This limitation arises because the outputs sampled from the network could correspond to distribution that is not consistent with the sequence that the network is trying to generate. This issue was discussed in 2015, and the practical advantage of scheduled sampling over professor forcing is that scheduled sampling does not require the additional overhead of having to train a discriminator network. Actor-critic methods have also been explored for improving modeling of long-term dependencies in generative recurrent neural networks. Ben Bahadarao, 2016. Finally, the idea of matching the behavior of the model when it is generating in free running way and when its behavior is constrained by the observed data that being clamped on the visible units is precisely that one obtains zeroing maximum likelihood gradient on undirected graphical models. Let me backtrack a little bit. It's precisely that which one obtains when zeroing maximum likelihood gradient on undirected models with latent variables such as Boltzmann machine. Training Boltzmann machines amounts to matching the sufficient statistics, which summarizes the behavior of the model in both teacher-forced and free-running modes. Okay, experiments, network architecture and professor forcing setup. Okay, teacher forcing, so we have this figure 1, architecture of the professor forcing, learn correct one-step predictions, such as to obtain the same kind of neural network dynamics, whether in open loop, teacher forcing mode, or closed loop generative mode. An open loop generator that does one step ahead prediction correctly. Recursively composing these outputs does multi-step prediction closed loop and can generate new sequences. This is achieved by train a classifier to distinguish open loop teacher forcing versus the closed loop forced learning dynamics as a function of sequence of hidden states and outputs. Optimize the closed loop generated to follow the classifier. So here they say they actually use both hidden states and outputs. Optimize the closed loop generated to fool the classifier. Optimize the loop generator with teacher forcing. The closed loop and open loop generators share all parameters. Yeah, obviously, yeah. I guess they mean here that the both networks are the same. They differ only in the mode that they execute in. So here they have, we'll go through these quickly, character level modeling. And figure 2, Penn Treebank likelihood curves in terms of number of iterations, training and executive lock likelihood on the left. Yes, and we can see the professor forcing, converges faster. The loss decreases faster. Sequential MNIST, T-SNE visualization of the hidden states. Left with the teacher forcing, right with the professor forcing. Red dots correspond to the teacher forcing states, while the gold dots correspond to the free running mode. Yeah, so on this picture they show that when they run the professor forcing, the dots are more mixed. It's harder to distinguish between the two modes, which is the sort of goal. Handwriting generation. Figure 5, handwriting samples with teacher forcing top and professor forcing bottom. Note that in both cases, the model is only trained on observed sequences all length 50, few letters, but it is used to do conditional generation for 1000 steps. Okay, so what they tell us about the figure 5 here. I don't see this. They don't reference the figure, or I don't see it, but I think here they send and authenticate Both models have equal train time samples using the same procedures. Varieties were not aware of the model. Yeah, it seems that from the experiments, the professor forcing was slightly better. Using synthesis on raw waveforms, again, they show faster convergence. Quality score, the professor forcing here seems to do almost twice as well, somewhere between 4/3 or twice as well. Negative results on shorter sequences. One word level Penn Treebank did not observe any difference between teacher forcing and professor forcing. One possible explanation for this difference is the increased importance of long-term dependencies in the character level modeling. Also, for speech synthesis, we did not observe any difference between teacher forcing and professor forcing while training on sequences of lengths less than 100. Okay, I'm gonna read conclusion once more. The idea of matching behavior of model when it's running on its own, making prediction, generating samples, etc. when it's forced to be consistent with the observed data is an old and powerful one. In this paper, we introduced Professor Forcing, a novel instance of this idea when the model of interest is a recurrent generative one, which relies on training an auxiliary model, discriminate spot differences in behavior between these two modes of behavior. Major motivation for this approach is that Discriminator can look at statistics of behavior and not just single-step predictions. Forcing the generator to behave the same way when it's constrained by the data and when it's left generating outputs by itself for a sequence can be much longer in training sum up. This naturally produces better generalization of the sequences that are much longer than the training sequences, as we have found. We also found that it helped to generalize better in terms of one-step prediction, log likelihood, even though we are adding a possibly conflicting term in the log likelihood training objective. This suggests that it's acting like a regularizer, but a very interesting one because it's also greatly speed up the conversions in terms of number of training updates. We validated the advantage of professor forcing over the traditional teacher forcing on a variety of sequential learning generative tasks, with particularly impressive results in acoustic generation, where the training sequences are much shorter because of memory constraints than the length of the sequences that we actually want to generate. Okay, that's all. Please let me know if you have any suggestions for future papers or anything regarding the videos. Never ever subscribe or like the videos, right? And thank you very much for staying till the end. See you next time.